one of the places I didn't get to was some of these word problems here about falling objects and so forth. I thought I'd grab one of these. Look at this 54. So I'm in 5-1, and 54 is a classic. They say, with what initial velocity must an object be thrown upward? Hold on just a second. They asked for with what initial velocity, so I'm writing that down. Seems like that's what they're asking for. Must an object be thrown upward from ground level? They want to reach the top of the Washington Monument, 550 feet. I don't think you're supposed to do that. You can't go hang around Washington and throw shit at the Washington Monument. You might get in trouble, you know what I mean? I don't know, especially nowadays. But anyway, that's what they did. They wanted to throw this object, and they wanted to reach the height of, they wanted it to reach the height of the Washington Monument, which is 550 feet high. And they want to know the initial velocity. So, what am I dealing with here? I'm dealing with the good old height equation, which is negative 16t squared plus v naught t plus s naught. Maybe I should memorize that. What's in chapter 2 or 3, it was chapter 3, we learned about this. And we learned that if we took the derivative, we would get a velocity equation, which is negative 32t plus v naught. Right, you guys? The derivative. And then if I took another derivative, I'd have an acceleration equation, which is negative 32, the next derivative. Which, by the way, is in a problem like this, it's just gravity. You know, we'll deal with some other problems where we have sort of horizontal acceleration, like me driving my car or running or something like that. Anyway, that's not gravity. That's some horizontal acceleration. But objects that are falling toward Earth experience this acceleration. Good old gravity is what it is. So anyway, this is old stuff. This is old chapter 3 stuff. Height, the derivative is velocity, the derivative is acceleration. What was new here in chapter 5 was, oh, you could start with this acceleration and you could integrate. You could start with acceleration, you could integrate to get velocity. And when you integrate, you get negative 32t plus c. And then we learned that the plus c is really just the v naught. Anyway, you could integrate again. Watch how you integrate again. You get t squared over 2, right, you guys? And then v naught t, and then another plus c. And it turns out that plus c is s naught, the initial height. So do you see that? I don't want to really do that every time I do one of these problems, but that's kind of the idea. The idea is you don't necessarily have to remember these anymore. You can start here and you can derive these by integrating. But I got it memorized. So in a way, you know, that integration is sort of behind the scenes there. I mean, now, this is not a problem about integration. It's about falling objects or throwing objects up. Or I mean, it's a little word problem here. It's not really about integration. The integration is kind of behind the scenes in the derivation of these formulas. So anyway, you know what I want? I mean, but to do these problems, I think you need to be staring at these equations. I think you need to stare at these equations and figure out how to use them. I mean, one thing I'm going to do is, if I'm going to hit the height of the Washington Monument, I think the height should be 550. So that height should be 550. So I'm going to write that in. The height should be 550. This is negative 16t squared. This, I don't know v naught. In fact, that's what they're asking for. Do you know s naught in this problem? Do you know s naught? I don't know. You might not have read it too good, but yes. S naught, they said I threw it up from ground level. So the initial height from where I threw this was 0. Yes. Cool. I'm just going to write s naught as 0. Just get rid of that there. Cool. All right, so there's an equation. And look at this equation. It has 2 variables. I mean, I'm supposed to find v naught, but I don't know t. So I've got 2 unknowns. You know, if you're staring at an equation with 2 unknowns, maybe you better go find another equation, which might mean you need another idea. And the idea here is that I want to hit the height of this Washington Monument, and I think it said I want it to be max height. And that's an important idea. Is that what it said? Yeah, didn't do a good job of actually saying max height. But listen, if you're going to hit this height, first of all, they don't want it to come up short. Then you wouldn't hit that height. And if you threw it too hard, you would go past it. That's not what they want. So they want it to hit that height and stop and turn around and fall back down, which means they do want that to be the max height. And what happens at max height?
Stop moving for a second.
You stop moving for a second. In other words, this is 0. The velocity is 0 when you hit max height. So that's your we need this second idea. We want the height to be 550, but when we reach that height, we want it to be max height. We want to stop for a second. So I want the velocity equation here to be 0. I want my velocity to be 0, and I want my height to be 550. That's the concept. And now it turns into an algebra problem. You got 2 equations with 2 variables. Please find V naught. They don't even care about t. They just want you to find V naught. Are you guys with me? I mean, it's a word problem, and they're difficult because they're words. But the hard part might be interpreting the words into the math. Once you do that, the math isn't that hard. Let's see, what would I do here? The easiest thing to do might be move the 32t over, and V naught is 32t. But then if you go substitute this in, where do I substitute this in? Right there? Then I get 550 equals negative 16t squared plus, that's 32t times another t, so that's a 32t squared. Are you guys with me? So if I continue working here, I'm going to find t, which is not what they wanted. But that's okay. Once I find t, I can plug it back in there and get the V naught. That's what they really wanted. You with me? So I can continue this. This is not bad. When I add those up, that's a 16t squared. That's 550. Divide by 16. T squared is 550 divided by 16. Everybody knows t is the square root of 550 divided by 16. To find V naught, it's 32 times t. 32 times this t. How are you guys doing? You all right? Did I talk too fast? See, I thought the hard part was interpreting it into math, and then I said, oh, now the math's easy. But you're staring at me weird. So maybe the math, I mean, I just solved, substituted, and solved for t. That was easy, I think. Divide by 16, take the square root. I mean, maybe you're worried about simplifying it somehow. I don't care about that. It's a number, it's a decimal number. There it is. Decimalize it, multiply by 32, and maybe tell me the answer here.
187.6166304.
Okay, thanks. I might call that 187.62 feet per second. This is 54. I'm not sure what the answer is. Do you guys trust him? Is he right? Can you? Yeah. Okay, cool. All right, cool. That wasn't too hard. That wasn't too hard. There's other problems. There's some more difficult ones using acceleration. Can I show you my favorite problem? Let me show you my favorite problem now, and I'm going to make it up though. It's not like it's similar to a couple in the book, but I'm just going to make this up. You ready? All right. So this is my favorite problem. And so my favorite problem is I'm walking. I went for a walk in my neighborhood, and I saw a bear. So there was a bear here. Cyclops bear. See that? Anyway, the bear was here. Here was me. This was me. And it was scary, you know. So I stopped and I got scared. And the bear was kind of scared too, actually. And we stared at each other for a minute. And it turns out we were, let me think here, we were 180 feet apart at the moment I saw him. Well, all of a sudden, he started chasing me, and I started running away. At the exact same time, I started running away with an acceleration. I ran this way. I started running away with an acceleration. No, I didn't run toward the bear. I ran away from the bear with an acceleration of 5 feet per second per second. And at the very same moment, the bear started chasing me with an acceleration of 8 feet per second per second. So if you know a little bit about math, you realize this ain't going to be good.
No.
Right. He's going to catch me, right? Okay. Well, maybe. I don't know. Let's see. I'm running toward my house. Let's check this out. My house is, if I can make it, this is my house. So if I can make it to my house, I don't know, dude. My house is, I don't know. My house is 320 feet away. This might not be good. I'm worried. I probably should step on the gas. What's the question?
How long till the bear catches you?
Yeah, maybe. When will the bear catch me? Right, that's a good question. If he catches me, when will he catch me? Right. Yeah, good question. When will he catch me? And so what does that mean? When will he catch me? I mean, what interpret that, please. When will he catch me? What does that mean? Duh, it means.
How long will it take for him to reach you?
Well, yeah, right. The time. I guess I want the time it takes. I guess I'm asking for the time it takes for him to catch me. But what does that mean? Catch me. Catch me means our accelerations are going to be the same, or no? Our distances should be the same. Our distance. All right, he'll catch me. So his position will be the same as my position or distance. This is not height, by the way. We're not falling off the moon or anything like that. We're running sideways. Look, for the bear, can you get the bear's, you got his acceleration. Can you get his velocity formula? How do you get velocity out of acceleration? You integrate, right? You integrate? Okay. So it's 8t plus some constant, but the constant is the v naught. And what is the bear's v naught?
0.
Yeah, good. He was just standing there when he started to accelerate. By the way, so was I. I was just standing there when I started to accelerate. Hey guys, I feel like you're doing some other stuff. Please, I like attention. I'm sorry, I'm an attention freak. I need your attention. I need your focus. If you're going to sit in the class, please give me your focus. Let's focus on the stuff I'm doing. I'm trying to teach you, explain stuff to you. So that's what I want and demand, please. Otherwise, go do something else. It's totally cool. Thank you. I would say his velocity is just 8t. Is that what I'm saying? Okay, cool. What about his distance? How do you get his distance?
Integrate again.
Integrate again. 4t squared plus some constant. That constant is his initial distance. I don't know. Look, there's a bunch of damn numbers on the board. At some place, you should call some place 0. What do you want to call 0? You could call my house 0. And then, I don't know what I am, negative 320. And let's not call my house 0. That doesn't make sense. What do you want to call 0?
The bear should be 0.
The bear could be 0. Okay, cool. So the bear is s equals 0. So what am I?
S equals 180.
I'm s equals 180. What's my house?
X equals 400.
Almost.
500.
Yeah, I guess so. I guess when I put this 320 here, I meant that was from me to the house. That would be another 320 added to the 180. Right, I think my house would be s equals 500. You guys okay? Okay, good. All right, so cool. Now wait a minute. So what is this? This plus c for his position, the bear's position. The plus c is his initial position, which is what?
0.
Okay, cool, 0. All right, then I got a position function for the bear. I think I'd like a position function for me. Let's see, let's do this. I'm going to integrate and get my velocity. What's my velocity? 5t plus my v naught, but what's my v naught?
0.
0. I could have switched it up. I could have said I was walking already. I could have said I had an initial velocity when I saw the bear, but I didn't. I said I was stopped, right? Me and the bear stopped. We stared each other down. Yeah, okay. All right, so my initial velocity was 0. Let's find my position. My position is you integrate and you get position. How do you integrate? Right? Plus S naught, or plus C, and the plus C for the position is the initial position of me, which the way I've decided to scale this is
180.
180. Cool. This isn't hard. And it sounds like a very hard word problem, but I gave you their accelerations. You integrate very quickly to get their velocities and their positions. And here's what when will he catch me? When my position
It's equal to his.
equals his position. And it's fairly easy algebra here to do this and find out when they're equal, right? Let's find it. Let's see, what am I going to do? Maybe I'll subtract the 5/2 t squared. If I subtract the 5/2 from it's a 2.5 from the 4, I think that leaves me 1.5 t squared. I think I'll divide by 1.5. If you divide by 1.5, can you help me? Really?
Yeah.
120? So then you take the square root, and t is whatever the square root of 120 is. Help me out.
10.95.
All right, thank you. Yeah, practically 11, right. Okay, 10.95 seconds, he catches me.
Wow.
I got my last 11 seconds of my life.
He could be a small bear.
That's true. Maybe I'd chase him. Maybe I'd chase him. He's a small bear. I need a new teddy bear anyway. I'll just chase him. Well, that one's kind of worn out. All right. Well, anyway, that's when he catches me. Unless, what?
You get to the house.
I'm in the house, right, and he doesn't know how to open doors and stuff like that. I wonder, did I make it? Did I make it to the house? How do I figure that out?
Would you plug that in for T?
Yeah.
Okay, so I found the time he catches me. If I plug that time in here, I can figure out where I'm at. If I'm at 500 or more, I guess I'm sitting in the house. Let's see what happens. If I plug this time in here, that's 5/2 times the square root of 120 squared, if you don't mind, plus 180. And I don't think I made it. I don't know. Let's see. The square root of 120 squared is 120. 5/2. Oh, maybe I did make it. 5/2 times 120 plus the 180. Let me see. That's 300.
480.
Shit. It's 480? Damn, I didn't make it.
Why didn't you ask that?
It was long. I should have called this a little. I should have.
300.
So he caught me right here. But you know what we did though? When he caught me, I turned and looked at him, and we stared deep into each other's eyes. And could tell we were both living beings. You know what I'm saying? We didn't need to. We didn't have to resort to violence. We kind of understood each other and loved each other. Yeah, peace and love. We had a moment. I like that question. It's easy in a way. It's easy, but anytime I bring up acceleration, velocity, students tend to freeze up a little. I'd like you to practice and not freeze up. I'd like you to.
I kind of like it.
Yeah, right. It's a fun little problem in a way, but it's easy to start with an acceleration and integrate, I think, and get these equations and find out when he catches me, and then right. All right, so there's more. There's some similar to that. 67 and 68 are very similar to this. The 65 and 66 are a little strange. They're a little tough, but I assigned 67 and 68 in 5-1. Hey, let's do something else now. In 5-2, do you guys need me to add up any rectangles? Are you good with that? Good, you're good with that. In 5-3, I did some of that homework. I think I want to do 5-4. I think I want to do this question. Look at this question. I think this is a 5-4 question, but it's a good one. You ready? I want to find the area of the region. This is how these questions are worded. I haven't really done one like this with you. Find the area of the region bounded by the curves y equals 0, y equals x squared, and hang on. 2x plus 8y equals I'm sorry. X plus 4y. X plus 4y equals 18. See, this is a good question. Again, I hadn't really helped you with this exactly yet, but here we go. We're easing into 5-4 here. We know if I want to find area under a curve, I mean, I've got this idea. I've got this idea that if I'm looking for area under a function from A to B, how do I do that? How do I find area under a function? I do an integral from A to B.
Right.
Right, you guys? I mean, this was a big concept. That's how you do it, right? That's how we do area now. Once you're past adding up rectangles, that's how you do area. It's a big idea. We haven't done too many. I did, one or two with you. But here we go. And this is a good question. I made up a good one. I didn't make up a baby one here. This is a good one. I think in order to figure out how to set up the integration, I need a good picture of this region. I want to find the area of this region. The boundaries of the region are these curves, or lines, or curves, or whatever they are. But these are the boundaries of the region. I think I need a darn good picture of this region. And then I can set up the integration to find the area. So a lot of this is making a good picture, maybe using your graphing calculators. I don't know. Can you tell me what y equals 0 is? That's one of my boundaries. What's y equals 0?
The x-axis.
Thank you, the x-axis. Right, so that's a boundary. That's what that is. Y equals 0 is the x-axis, right? So that's a boundary. What else is a boundary? Oh, good old y equals x squared is a boundary. That's a parabola. So that's one of my boundaries. Maybe my area is somewhere in between here, right? I guess. What's another boundary? Oh, another boundary is this line. This is a line, by the way. If I wanted to use my calculator, I'd have to solve for y and type it in my graphing calculator. It's just a line, though. Let me think here a second. If I let y equals 0, I think it hits the x-axis at 18. Do you agree with that?
Yeah.
If I let y equals 0, it hits the x-axis at 18. Huh. If I let x equals 0, it hits the y-axis at 18/4, or 4.5. That's this line. So that line is a boundary. This parabola is a boundary. This is a boundary. Have you figured out your region?
Yes, that triangle looking thing.
This sort of thing, yes. This is it. A lot of people, when you have a problem like this, one of the big problems is they'll shade the wrong region and go start working on the wrong region, and that's disastrous. I mean, it's hard to give you too much partial credit for that. You need the right region. And so pay attention to what the boundaries are. Don't assume other boundaries that aren't there. You know, if they wanted it to be this region, they would have said x equals 0 is a boundary. This is called x equals 0. Anyway, they didn't. They said y equals 0. They said that line. They said that parabola. This is it, dude. This is the region. And according to this, you know, you can get area under a function if you just integrate that function. That's all you do. You just integrate the function that's sort of that's your top or your ceiling or whatever. And then you get the area underneath it. Do you see a problem with this?
I have a question.
So who's the function? Who's my ceiling? Who am I integrating? And I think you should say you have two ceilings. You have two ceilings. You have this function called x squared, and then you have this function, which is the line. And I think if I want this area under this parabola, I think I should stop there and shade this and calculate that area. Then I think I should maybe maybe do another integral where I calculate that area. Do you agree? And then maybe add them together to get the total area. Are you with me? That's what you have to do on this problem. Sorry, I stepped it up a notch. Instead of just giving you one function to find the area underneath, I gave you two functions. And so we gotta sort of split this up. Damn, you know what I really want to know? I really want to know where this is. I know this is 0. I know this is 18. What's this, I wonder? I mean, what do you think I need to do?
Find that point.
Find that point of intersection?
Yeah.
How do you find a point of intersection?
Put in x squared for 1.
Oh, I guess I could. Y equals x squared. It's like I need to kind of set these equal to each other, right? Or solve this. Where do these two guys intersect? I can set them equal to each other, or I can substitute somehow. I like what he said. If y is x squared, can't I just plug in an x squared right there?
Yeah.
All right, what does that give me? It's a quadratic equation. Do I know how to solve a quadratic equation? Yeah, I do. All right, plus the x, move the 18 over, make it equal to 0, use the quadratic formula, or maybe it factors. Geez, I hope I made this up okay. This is maybe a 2x and a 2x, maybe a 6 and a 3, 9 and 2.
Doesn't really work.
This ain't working too good. Maybe it ain't 2x. Maybe it's 4x and 1x. Is that okay with you? 4x and 1x, maybe 9 and 2. 9 and 2! Dude, a positive 9 and a negative 2. I got it. It factored. I got it factored. It factored. So the answer is when x is 2 or when x is negative 9/4. Hey, which one do you think I'm looking for? Negative 9/4 is way over here. That must be where the line intersects the other part of parabola. Yeah, I guess I'm not interested in that. I'm interested in x equals 2, I think, right here. Awesome. Yeah, I found the x value to be 2. The truth is, that's all I care about is that x value. If you plug it in the function, though, the y value is 4. All right, here we go, guys. Can we find this blue area? I need an integral. Actually, I think I need two integrals. Is that what I said?
Right.
You get that? What's my first integral going to be?
0 to 2.
0 to 2, and who are you integrating? That function, the parabola. So you're going to set up an integral from 0 to 2. You're going to integrate the parabola, and you're going to find that area. You with me? See, can you see the picture and see the integral? That's what you got to see the picture, see the integral, and have it make sense. It makes sense. Then I think we'll go from 2 to 18. From 2 to 18, and now who am I integrating? The line. Okay, the line is x plus 4y equals 18. You know, when you put this function into the integrand, what do you put there? You put,
You have to get y by itself.
yes, you put the function in there, which is y. Right, you need to solve for y and put your function in there.
Okay.
Are you guys with me? This is a good problem. This is a good problem. I need that function in there. Let's see, I'll subtract x and divide by 4. If you don't mind, 18 minus x divided by 4. Is that okay with you? All right. Whew. You know, sometimes I feel like that's the hard part. Setting this all up. Reading this, drawing the picture, figuring out some calculations. This is a darn good picture. You need a darn good picture with darn good labels. You know, I needed to figure out that was 0, 18, and 2. I had to get this, I need a good picture. And then when I see it well and create this great picture, I can set up my integration. And then I sort of feel like the rest of this is easy. Oh, you can do the rest of this, but the truth is you're very, very, very new at this. Maybe you need help with this. You're very new at this. You may not have ever done one. So let's do it. You ready to do it?
This is kind of from 5.3.
So how do you integrate x squared?
X to the cube over
Good job.
3.
That's it, right? Is that right?
Yeah.
So you have to know how to do that. And then,
Yeah, from 0 to
and then what? Here's the new part of 5.4 that I've alluded to 2 or 3 times, but it's very new until you get to 5.4. Now you evaluate from 0 to 2. And that means you plug in the 2, which is 8/3, minus you plug in the 0, which is 0, and so the answer is 8/3. Again, that's only half the answer, so to speak. We got to work on this other integral over here. Right, you guys? Listen to this. I haven't done this much with you either, but I'm gonna talk to you here. You can, one thing you do with integration is you can pull out constants. You can pull a constant out in front of the integral. You can pull a constant out in front of the integral. We did that with derivatives, and it's useful sometimes with these integrals. I want to pull out a 1/4. Yeah, I got to be careful when I say that. I say you can pull out constants. Listen, they have to be multiplied constants. They can't be not added constants. You can't pull out the 18. The 18 is its own separate term. That's bad. That's bad. That's bad. But I got a multiplied 1/4 sitting there. Do you agree? I can pull out a 1/4. That's what I'm doing. Now, I'm going to integrate the 18. Can you integrate the 18? I got the 1/4 out of the way. Forget about that. So now I got 18 minus x. So can you integrate an 18? 18x. Can you integrate an x?
1/2 x squared.
1/2 x squared. Okay, cool. Dude, that's awesome. You're finished. Except for evaluating this from 2 to 18. By the way, this last part is sticking in the 18, sticking in 2. I mean, it shouldn't be hard, but I swear to God, this is a great place for mistakes. I mean, you know, you gotta finish the details here. If you plug in the 18, you have, what do you have here? You got 1/4. 18 times 18 is 324 minus 18 squared divided by 2. That's 324 divided by 2. That's 162. That's me plugging in the 18. Nice and quick. Minus 1/4 in front of. Now I'm plugging in the 2, you guys. I'm plugging in the 2. That's a 36. And that's a 4 over 2, which is a 2. when I plug in the 2. You guys, okay. I integrated. I plugged in the 18. I plug in the 2. I subtract those. That's good. I mean, that's the proper setup. That's the proper, I'm writing down all my steps there for you. Now I got to do it. 324 minus 162 is 162 divided by 4. Everybody knows 162 divided by 4 is 81 halves. That's an 81 halves. Minus, what is this over here? That's an 18. No, it's not. What an idiot. That is a 34. 34 divided by 4. 34 divided by 4 is 17 halves. So this is 81 halves minus 17 halves. Everybody knows that's 64 halves. No, 64 halves. 64 halves is 32. That's a big old 32 right there.
So you have to add 8/3.
So that's a 32. This is an 8/3. And so, which by the way is 2 2/3. So the final answer is 34 2/3. Woohoo! Wow. That's good stuff. I need a 2-minute break. I appreciate your attention. Hang on.